Thank you very much, and thanks a lot for the invitation to speak here today at this very nice conference. Already heard a couple of very interesting talks, and I'm looking forward to the rest of the conference. So, yeah, my research group is working on the interface between machine learning and AI methods development in the computer science department of KIT, and various application areas in molecular and materials design, in atomistic simulations of molecules and materials, and between the interface of AI and machine learning methods development and directly coupling them to experiments. And we've already heard quite a lot on that side today. And my talk will focus on two different areas here. So I will first talk a bit about how we can use machine learning models to virtually predict materials properties, molecular properties, design new molecules and materials, and also understand better structure property relations. So we get scientific understanding that we can then use for more rational design of new materials and molecules. And in the second part, I will show how we can directly interface such methods with experiment to accelerate the experimental scientific progress. So one of the big challenges and also opportunities that we have in material science and chemistry is the vast size of the chemical space. So if we look at even conservative estimations of how many small molecules we can in principle make, we have estimations of 10 to the 60. If we look at material space, of course, this is even like exponentially larger because of the availability of more elements, more compositions, and so on. And if we now look at what is currently known, for example, if we look at chemistry, the PubChem database reports roughly 100 million compounds that were reported in scientific literature so far. If we compare this now to 10 to the 60, even though 1 million sounds quite large, it's only barely scratching the surface of the full chemical space of different molecules and materials. And of course, we have to admit that most of these reported compounds were actually found using experimental procedures. So experimental exploration of this chemical space is the standard right now. But we, of course, should also ask the question, can computational methods help us in screening this space and designing new molecules and materials? And it was shown in a lot of different studies that computational methods, simulation methods, and so on can help us accelerate this process by orders of magnitude by basically pre-selecting good molecular and materials candidates using physics-based simulations and simulation tools. Question now is, in this talk that I would like to ask is, can data-driven methods, machine learning methods, further speed up that search? And we've already heard quite some very nice examples of how, for example, Bayesian optimization methods and closed-loop discovery can help speed up the search for new materials and optimization processes by orders of magnitude. And I would like to also transfer this now to a more general setting of virtual screening and virtual design and property predictions of molecules. And in order for data-driven methods to really make a difference, we can look at two things here. Either we can use data-driven methods to exploit redundancies. That means we only do exactly the simulations, exactly those experiments that are informative, that are helping data-driven models to learn more, and basically avoiding everything else. Because whenever we create redundancies, we basically do experiments, we do simulations that are not really needed, and machine learning models, data-driven models can, in principle, interpolate nicely between them and thus speed up the search. And this can be exploited in a lot of different scenarios. Another thing I would like to discuss a bit more today, this was, I think, already mentioned by Alexander Hammer, or by the answer of the GPT model to his questions of how machine learning or how we can speed up material science, is by using machine learning models to uncover hidden relations in data. And also Larry talked about that a lot. How can we basically understand structure in high-dimensional data and extract that knowledge and make use of that in order to better understand structure property relations and better understand how we can rationally design better molecules and materials. So in the first part of my talk, I would like to discuss a bit of the work on virtual design that we do in our lab, mostly based on work by a postdoc in my group, Patrick Reiser. And then in the second half, I would like to discuss a bit more how we can interface machine learning methods with experiment. And I will talk here about 2 different collaborations, one with Manuel Tutsalas on metal organic frameworks and one with Leonardo Velasco on high entropy oxide. So not directly related to photovoltaics and solar cells, but it's also more generic and transferable to the application area of solar cells. Let's start with the design, virtual design. The first question we have to ask here is, how do we bridge or bring together molecules and materials on the one side and state-of-the-art machine learning models on the other side? So on the one side, we have molecules, we have in principle assemblies of atoms in space. So we have atoms and bonds and their positions in space, 3D point clouds basically. On the other hand side, we have typically neural networks that require something as vectors, as inputs in order to predict certain properties. We have, for example, convolutional neural networks working very well on grid-like data, on images, on videos, where we can basically have our data presented, or the input data presented on a grid, like pixel values in images. We also have recurrent neural networks and sequence-based models that are very, very efficient in, for example, natural language processing, in, for example, translating what I'm saying into text, or translation between different languages, or even like chat robots or chat machines that we discussed earlier. But the big question is, how do we bring that together? How can we make use of all these advanced machine learning methods also for chemistry and material science? And of course, there's various different ways of how we can basically translate between the input that we actually have, the 3D point clouds, 3D materials in space, to, for example, vector type of representations. We can, for example, extract features from the molecules and materials that we know are hopefully correlated with the target properties that are costly to compute or to experimentally identify. So we can make use of the knowledge we already know and make use of these features and also learn a lot from that. And then, for example, translate a molecular material into a vector and then use typical neural network, Gaussian process models, and so on that need vector type input. Sometimes in chemistry, we can also represent molecules as sequences, for example, as Miles codes. So we can make use of these language models, the sequence-based models, in order to translate or to learn representations from the sequence input into some sort of vector space from which we can make predictions. In the last couple of years, a new method was coming up, and it's like right now exponentially exploding in research activity. It started roughly in 2015 with a paper by Duvenot et al., where it was suggested that we can basically turn around the problem and say we need to adapt the machine learning models to the input data that we have at hand. So can we work directly on the input data, meaning on 3D structures, 3D assemblies of atoms in space? The idea is that we want to somehow represent arbitrary point clouds. So we have different materials, different molecules in different sizes, and we need to learn a model that can fit them or translate them into a feature vector. And the idea is we represent atoms as nodes in a graph and edges or bonds between the atoms or distances between the atoms as edges in a graph. And then we define a graph neural network that can work on this graph or 3D type of input to learn first atom representations. So the graph neural networks first have the task of learning what is the local environment of atoms in a certain molecule or material. And then in the second step, it combines all of these learned atom representations into a learned molecular or materials representation, where the geometry information can be fully included. We don't have to define the features ourselves, but the model has to extract features that are relevant for the prediction task at hand by themselves. And these models reach state-of-the-art performance in probability prediction tasks. And here the bracket here is very important for large data sets. And thanks to a lot of initiatives in large databases and data collection, we, for many applications, have large data sets now. However, if we talk about directly interfacing to experimental data, of course, we don't always have large data sets, and large means here like a couple of hundred data points at least, better a couple of thousand of data points, which we of course not always have. And then we have to combine such purely end-to-end learned model with still our insight, our features, and so on, in order to make good predictions. So our lab is focusing a lot on developing and using these graph neural networks. So among others, we are developing a graph neural network-based library, KGCNN, that should be available to researchers who are also non-experts in developing such models, and it should be able enable you to basically load your data sets and train graph neural networks yourself in a relatively easy manner. Same time, we work on a couple of different collaboration projects where we look into, for example, using graph neural networks to predict reaction barriers for chemical reactions. We look into organic electronics also, which is relatively relevant for solar cells here. So we look into how can we enhance graph neural networks with quantum chemistry information that we can easily compute, for example, using semi-empirical methods in order to inform the graph neural network on top of just the 3D information, also on quantum mechanics information, for example, HOMO and LUMO orbitals. So the model can learn more intuitively what are relevant features to extract from the molecule and its wave function in order to make predictions. You can also transfer this to solid state materials, periodic structures, for example, superconductors, where we work with Jörg Schmalian here at KIT, and Timo Sommer was mostly driving this project on generating a data set of 3D structures of superconductors in order to see whether we can learn interesting structure property relations from such data sets. If you're interested, one more slide here. So the graph networks on crystalline systems, we are mostly right now focusing on typical benchmark data sets. For example, this MudBench benchmark from the materials project, where we are developing graph neural networks that exploit symmetries, make the graph neural networks more efficient in that way. And also we generalize the graph neural networks to some extent between graph neural networks specifically designed for molecular property prediction tasks and graph neural networks for the material science side. So we try to generalize this and basically exploit all the developments on both sides and combine them into one model, which is work done by Robin Ruff here. So if you're interested in such graph neural networks, how they work and how they also can be applied in a lot of different application areas, I would like to point out here a review paper that we recently published just a couple of weeks ago, where we show how graph neural networks work from a more basic principle perspective. And then we show a lot of different application areas on molecules, property prediction, on material science, property prediction, also in inverse design tasks, and also in the end on scientific understanding. So how can we extract knowledge from the graph neural networks to learn something for ourselves? And this brings me also here to the next topic I would like to quickly talk about. This is based on a paper that was developed over multiple years, mostly driven by Mario Kren's initiative, who is the first author here. And this is based on discussions and surveys that we did with a lot of different researchers in the field of computational materials design and modeling in the last couple of years. So we were asking more or less the question, how does AI and machine learning methods or computational methods in general contribute actually to more basic scientific understanding? So turn it around, we don't only ask the question, how can we use those tools to discover new materials or to predict their properties in a very accurate, efficient way, but more, what can we extract, what can we learn from the models? We did a survey among very large amount of scientists and asked them, how did computational tools, machine learning models help you in developing new insights? We found three sources of answers, or more or less two sources of answers. One was basically researchers were using machine learning models as a computational microscope. So the models were giving insight into what is going on, for example, on the nanoscale of systems, which is not easily observable with experimental techniques. So we basically use the machine learning model as a microscope to discover new things on the nanoscale and then make sense of these things and try to abstract rules that help us develop new materials and getting some intuition. Another thing was, a group of answers was, we can use computational tools and machine learning models as sources of inspirations. So the models can, in principle, help us to find very interesting examples that are basically opening our eyes. So if we look at the large data set and random samples of these random molecules with more or less mediocre properties, it's sometimes very hard to see the structure property relations. However, the models can be very good in finding extreme cases, finding outliers, finding molecules or materials with very high and low properties. And then if we look at these extreme cases, we can find interesting examples quicker. And then also from these, looking at these extreme examples, finding structure property relations that then help us again develop some intuition. the last group of things that we kind of hoped for, but we didn't really find any, let's say, evidence yet in the stories that we were told, was that the models are actually acting as agents of understanding themselves. And that would mean that the models not only look at the data, but they actually give explanations themselves and can somewhat teach us. Of course, what's limited here right now, and I think there will be a lot of exciting developments in the next couple of years, is that explanations for us are typically done in natural language. And for that, we need to basically couple machine learning models with natural language and also with some contextual information about the science that we assembled over years and decades where we studied our respective sciences and domains and basically generated a network of knowledge in our heads that machine learning models very often don't have access to. And we need that to generate explanations. I would like to show one step that we tried to go in that direction. So we were looking at the question, can we, is there a trade-off between the explainability of a model and the accuracy of a model? Because very often in literature it's discussed, you can either have a model that's highly accurate in doing their predictions or a model that's kind of explaining itself. And for that, you need to go to simpler models that are maybe not as accurate. So we wanted to see whether there's a trade-off. And the second thing we wanted to see is also, can we have models where we can not only teach the models with the labels that we typically have, but also with explanations. So if we have explanations, say we have a molecule, we have its property, and we can also have an explanation. This subgraph is relevant for this property. Can we teach the model? And this forces us to use a model that doesn't only generate the explanations post hoc after the training, by just analyzing and opening the black box, but we need a model that intrinsically generates the explanations and uses it themselves. So we can have some sort of explanation supervision. We can say, okay, this is the explanation. Please also use it and train yourself with that explanation. And this graph that I'm showing here is a neural network, a graph neural network architecture that we don't need to understand in detail here now. The idea is we use graph attention layers. They can look at what is the importances of certain edges in the prediction. So we can use these importances generated using these graph attention layers to make edge explanations. We can then pool those into node explanations. So we get explanations not only for the connections between atoms, but also for the atoms itself. And then the interesting part is we feed back that thing. That's this one tiny looking arrow here that feeds back from the explanation into the prediction channel. So we force the model to only focus on the explanations that it produces, rather than making independent explanations and predictions. So if the model says this is important, this subgraph, this submolecule feature or submaterial feature, then it has to focus on that when it's doing its prediction. So let's look at an application use case. We now see here a couple of molecules. So we trained this model on water solubility, and we don't only get one explanation channel, but multiple explanation channels if we want. So we can have one explanation channel, this is the upper channel here, where the model is now generating explanations for what are relevant structures for low water solubility, whereas the lower row here is for high water solubility. And this is also very different than the post hoc explanation models that are typically only generating importance maps. So they only say this subpart of the molecule is important for the prediction of water solubility, and then it's on us in the end to figure out what is actually meant with important and what leads to what correlation. So we see that we can recover a lot of chemical intuition in water solubility. For example, we have here long alkyl chains that are not very water soluble, whereas this more polar part of the molecule is water soluble, and so on. So this kind of creates consistent explanations with what we already know. We apply this now also to OLED molecules, in particular molecules for TADF. So we want to have molecules that have a very low splitting between the triplet and the singlet gap. And then we predicted this singlet triplet gap and also asked the model what is now relevant for high or low singlet triplet gaps. And we again see very interesting, very distinct groups where the model sees, okay, there's a strong correlation between a certain direction in that gap. For example, we see that these conjugated bridges here that are used in a lot of TADF molecules are actually increasing the singlet triplet gap, whereas other groups, for example, amines connected to different aromatic rings, are lowering the singlet triplet gap, which is again like correlated to knowledge that's already known, but we also found a couple of motifs that we can now further interpret and connect to our scientific knowledge of what might be the cause of such a correlation. We can here have now a model that, and I missed to mention that this model now also shows quite accurate prediction power. So it's not a trade-off. This model is also beating state-of-the-art models to some extent in the predictive accuracy. So we actually don't have a trade-off between explainability and accuracy. And of course, always up for challenges. So if you have a challenging data set, maybe on molecules, maybe on also solid state graphs, we're very happy to look at such a data set with our model to see what is the accuracy of the prediction, but also mainly to see what are the explanations that the model comes up with, and what are the structure property relations that such a model can extract from the data. So if you have any idea here, feel free to reach out to me and we can discuss that. With this, I would like to switch over to the second part of my talk. So how can we now go from all these virtual design methods to predict properties and to maybe also generate scientific insight and explanations over to how can we couple them to experiment. We've already seen that diagram or another version of that a couple of times today. So when we talk about coupling machine learning and material science or chemistry experiments, we typically include a third part here into that, which is the automation. So we have interesting challenges in chemistry and material science. We automate the labs to some extent and then loop in or close the loop using machine learning approaches that can do the next step. And very often, we saw in the past that this is shifting the bottleneck from something that was a bottleneck before to kind of new bottlenecks. Very often the new bottlenecks are related to either data analysis, so we're generating large amounts of data on the fly that typically was not available in that quantity before. And typically it was analyzed by humans, by actual researchers. And now we would like to kind of automate that data analysis step, which can sometimes be quite demanding in terms of time that is invested into that. For example, if we think about the analysis of XRD diffractograms, which can take hours or even days to do for a single diagram, we would like to have now models that can process that data and analyze the data more or less automatically or with a human in the loop to have a pre-selection. Also, synthesis is suddenly becoming a more important bottleneck. So if we want to explore new materials, we need to also predict what is their synthesis, not only what is the characterization and their properties, but how can we even synthesize them. I'd like to show a couple of examples of that in the next couple of slides. So one of the bottlenecks, as I already mentioned, that we identified in a very nice high entropy materials acceleration platform that was developed by Leonardo Velasco, who was at KIT until recently. He's now professor in Columbia. He was developing this platform that can automatically synthesize high entropy oxides from solutions. And it includes also a couple of characterization steps, such as UV-Vis, XRD, Raman spectroscopy, and so on. And the synthesis is speed up in a way that it can do up to a couple of hundred samples every day and hundreds of samples every week. And also it can do even XRD analysis of more than 100, or in this case, more than 300 samples every week. And if we now generate that amount of data, so many XRD diffractograms, of course, the question is, how can we even analyze this? So how can we even analyze on the fly whether a certain high entropy oxide, for example, formed in ice, a single phase material, or whether it is integrated into multiple different phases and therefore is not a single high entropy oxide, but multiple different oxides that are maybe not high entropy anymore. And here we were pursuing a interpretable machine learning model that enables what we call human in the loop workflow. So the idea is not to fully automate that, but to basically have a very good and reliable pre-selection tool for human researchers to then select which of the data points do I want to actually spend my time on and look further into, and which data points do I want to just trust the machine learning model. And for this trust, we very often don't need only predictions by the machine learning model, but we need also, again, some sort of interpretations. And in this case here, the model was not only predicting whether an XRD diffractogram shows a pure or a mixed phase of a high entropy oxide, but it was also basically labeling in red and blue which of the peaks and which of the shoulders of peaks the model thinks are relevant for its prediction. So if the model, for example, says for this sample number 7 here, this is a non-pure phase, it's not a single phase, but multiple different phases, it labeled, okay, in red, all these peaks are telling me, okay, this is rather shifted towards the multiple phase side of things, whereas all the bluely labeled peaks are basically telling the model there's more evidence that it's a single phase material. And maybe this first peak is not so relevant. Maybe this is just noise or something that's easy to interpret. Maybe this shoulder of this main peak here, where there's some red thing, could be like an evidence where the human researchers can say, okay, I trust the machine learning model. There's probably something hidden in that shoulder. So I believe it's a multi-phase material. Or the researcher says, okay, this shoulder looks kind of fine. I don't need to see where's the problem. I'll look at that by hand and do all the analysis by hand, which may take a few hours, but then we have full control again over the experiment. We were thinking about how to generalize this further, and Henrik Schopmans, who was doing his master thesis now on space group classification for XRD. So not only on determining whether XRD diffractograms show a single or a mixed phase, he wanted to look at the more general task of mapping from an XRD diffractogram to any of the 230 space groups. We were first looking into what is actually the state of the art, and we saw that the ICSD data space has a large amount of data where people are training for exactly that task. So the input would be what is the XRD diffractogram, and the output what is one of the 230 space groups. So it's a classification task with 230 different classes. What we first saw is that there's some data leakage. So the researchers reported there's roughly 82% accuracy in that task, but we saw that if you just randomly split the ICSD data set into training and test data, then you might end up in some data leakage, because there's very similar crystals that then might end up both on the training and on the validation side. So if we make a more rigid, a more challenging split, we end up with the same model only achieving 56% accuracy. And then we thought, how can we improve that? And one of the ways of improving that is by generating synthetic data and not just relying on the data, on the ICSD data that exists, but creating basically synthetic crystals. So Henrik came up with an algorithm that on the fly basically generates an infinite stream of synthetic crystal structures, then simulates what is the XRD diffractogram, and then trains a machine learning model. And here we can go to very, very deep and large models. For example, this large model here with 41 million parameters, because we have this infinite stream of data that we can just use to train the models. And we see that the bigger we made the models, also existing models, but also this ResNet-inspired architecture, the better we get the accuracy. So we're almost again there at the accuracy that was reported with the not so good split. But now we are consistently using that more demanding split, and we're back up to roughly 77% accuracy in the prediction. And of course, this doesn't sound so great yet, but if we look at like the top 5 or top 10 prediction, we get much closer to 100%. And also we have to consider that everything is then tested, of course, on the ICSD data set, and the ICSD data set has also a lot of space groups that are very, very rare. And this, of course, is a challenging task for machine learning models. Last topic I would like to talk about before I come to the end of my talk was using machine learning models to predict synthesis conditions. And here we looked into a project on metal organic framework synthesis, and the typical approach, if you have a target MOF that was maybe designed by a computational workflow, and it was shown, or at least on the computational side, that it has very good characteristics, properties that are needed for an application. We basically need experts that go into literature and find MOFs that are somewhat similar, depending on what you define as similarity, and then start or extract good synthesis conditions to start a experimental trial and error process to synthesize that target MOF. And we were trying to design the data-driven equivalent of this approach. So we created the first MOF synthesis database. Of course, there's loads of different MOF crystal structure databases out there, but we were using an automated extraction protocol that was going through thousands of papers, extracted all the relevant synthesis condition for a lot of different known MOFs, and created a database, and then trained a machine learning model on the database that can map from the MOF input structure to the optimal synthesis conditions. So it uses just the CIF file basically as the input, as the structure, and predicts what is the optimal temperature, what is the optimal solvent, what is the optimal time to run that MOF synthesis. And the nice thing about here, this model refinement can, of course, now in an automated platform be again, for example, a Bayesian optimization algorithm. So we can start now a fine-tuning of these start parameters that our machine learning model predicted, and then create new data points on the fly in an automated way that enhance also our data set. and enhance our database so that future models will be even more informed about what is good starting structures and good starting synthesis conditions for such a process. This data set and also the machine learning model is publicly available. So if you want to include this model or a similar model in an automated synthesis platform, you can just use this web API. You can also manually use it by uploading, for example, a CIF file of a MOF structure, and then the model will predict in the background what is the temperature, time, and so on. But of course, if you're interested in transferring such a procedure to other classes of materials, I'm again happy to talk about that. We can collaborate on that direction. One very last slide. We're also currently at KIT in cooperation with Alexander Kolzmann and Holger Röhm and Wolfgang Wenzel are creating a new materials acceleration platform for energy materials, where we're combining in a modular way different stations. And the goal is here to look at a wide range of different materials classes, ranging from lead-free perovskites over superconductors based on ceramics, organic photovoltaics, and OLEDs in a closed-loop way, controlled by machine learning models and AI. And I hope that maybe in the next iteration of this nice conference, we can talk more about this. So with this, I'm at the end of my talk. I started with machine learning models that can predict materials, went into machine learning models that can give us some explanations of what the machine learning model actually learned. And then at the end showed some examples of how we can use machine learning to alleviate now some of the newly arising bottlenecks in automated platforms. So I would like to thank, of course, all the people contributing to this work, all the funding agencies, and I thank you for your attention.